Bismillahirrahmanirrahim. This is my lecture about the course of nanophysics and technology, having the course code of PHY445. And in today's lecture I will discuss something about the scanning tunneling microscope. The basic objective of today's lecture is to understand the history of scanning tunneling microscope, why it has been introduced and why it's beneficial from the other microscopes, the basic principle of STM, why is called as a scanning tunneling microscope, and what is this basic principle, the key component of STM, and at the end we will discuss the uses and application of scanning tunneling microscope. Generally, scanning tunneling microscopes come across the come in the family of scanning probe microscope. The scanning probe microscopy has mainly five different types of microscopies. The first one is the atomic force microscopy, what we had discussed in the last lecture. The second one is electrostatic force microscopy, is not included in our course. And the third one is the magnetic force microscopy, it is also not included in our course outline. And the fourth one is the scanning tunneling microscopy, that is actually the lecture today. And at the end we have a fifth type, that is the near field scanning optical microscope, that is also not included in our course. So what is the history of scanning tunneling microscope and why it has been introduced? Behind the development of scanning tunneling microscope, there are two famous names who got Nobel Prize in 1986. The first one is the Benning and the second one is Rohre. And in 1981 they developed the scanning tunneling microscope at IBM Zurich, and further in 1986 they had been awarded the Nobel Prize for Physics for these achievements. What is the basic principle of scanning tunneling microscope? As we see in the name, we have the two words, that is the scanning and tunneling. I mean, two phenomena used. Before going toward the working principle of the scanning tunneling microscope, we need to discuss some classical and quantum view about the tunneling. And we need to know the tunneling effect. Normally in classical mechanics, if the energy of a particle is smaller than the energy of the barrier, then it is impossible for the particle to overcome this barrier. This is classical approach. But in quantum mechanics, if the energy of the particle is even less than the energy of the barrier or the obstacle, still there is some limited chances that the particle may be found at the other side of the barrier. It depends upon the depth of the barrier. Here we can say the quantum mechanical approach, we have the particle having the energy even less than the energy of the barrier, but it has some limited probability of finding the particle on the other side of the barrier. And similarly in this case, because the barrier is thin, still it has some possibility that the particle will be there. So in scanning tunneling microscope is based on the quantum mechanical approach, and it deals with the unlike the classical mechanics, it deals with the microscopic levels. So we need to discuss the wave nature of the particle, and need to discuss the associated wave with the moving particle. So this classical and this quantum mechanics tunneling effect has been the basic principle of STM, and that is the phenomena that is occurring between the sample and the tip of the STM. Here tunneling effect is more explained in detail. Here this is the sample, the image of the sample, and this is the tip of the scanning tunneling microscope. Keep in mind the tip of the scanning tunneling microscope is nearly same like AFM, atomic force microscopy, but in this case actually there is no contact mode. There is no contact mode, and the electron from the sample may go to the tip of the sample, or maybe the electron from the tip of the sample go to the tunnel to the sample. So there are different biasing approach on this. In this particular case, we can see that the Fermi levels of the sample and the Fermi level of the tip, when the negative bias is applied, so what happen, the occupied state of the samples, the electron moves to the tip. Here you see the electron move from the sample to the tip, and occupied states of the sample are investigated. And what is the case when positive bias is applied? This is the second case. When the positive bias is applied between the tip and the sample, what happens? This is actually the vacuum is actually the space in between the tip and the sample. So as a result of the positive bias, electron will move to the sample from the tip, and in this case we will investigate the unoccupied states of the samples. So tunneling current is the most important phenomena which play a vital role in understanding this scanning tunneling microscope. In this case, normally we say that there is a specific work function for each metal, and work function is the minimum amount of energy that is required for an electron to leave the metal surface. So the electron need to overcome a barrier, that is a work function, to travel from the tip of the specimen from the tip to the specimen. And similarly, if an electron want to move from the specimen to the tip, again it need a work function. But if the energy required is less than the work function, so what happens? The electron will tunnel. Even that is why it's called as tunneling effect, because the energy of the electron is even less than the energy of the barrier. And what is the barrier? Barrier is actually the vacuum in between the sample and the tip. This can be done. The electron could be moved with the help of applied potential. Here in this case we can say that vacuum is actually in between the sample and the tip, and this is the work function, and some current is voltage is applied. So as a result, the electron tunnel from one place, from the tip to the sample, or from the sample to the tip, depending on the direction of the applied voltage. So scanning tunneling microscope, these are actually some of the images and the specification of the scanning tunneling microscope, because it has an electron microscope that transmit three-dimensional images. It is very different from the existing microscope like we had discussed, the scanning electron microscope, transmission electron microscope, and atomic force microscopy. It has this specialty of developing three-dimensional images of the electron, and its resolution is very high, is around 0.1 angstrom. So is atomic level. So it means the STM is a very important technique in determining the atomic structure of an electronic state of the surface under investigation. And the other specialty of STM is that it allows the observation of the property of conductive solid interference at an atomic size. But it has one problem, that we cannot investigate insulating material with the help of STM. So we can view the surfaces at atomic size due to the very high resolution of STM, and the resolution is around 0.1 angstrom. So these are some of the images of scanning tunneling microscope. It's actually developed three-dimensional images. This is very interesting to know the charge distribution and the atomic size and dimension of the different nanostructures. Coming towards the structure and the basic component of STM, there are mainly 5 basic components of STM. The first thing and the most important is the metal tip. There is also called as the metal tip, and this metal tip play a vital role in investigating or scanning the sample. The other is the piezoelectric scanner. This is actually the piezoelectric tube, and in this there is piezoelectric scanner. We have the vibration isolating tube. The whole system is called as vibration isolated system, because there is a piezoelectric sensor over there, and in piezoelectric sensor the applied voltage can create dimensional changes in the material. So it's very much important for us to develop the system such that it can have vibration isolated system. So it means one part of the system is if it is vibrating, so it cannot influence the other part of the system, otherwise the piezoelectric current may be produced due to that. or maybe the length or dimension changes occur due to that. And finally, the fifth part of this STM is the data processing unit. The data what has been obtained from the tip and that has been forwarded toward the piezoelectric tube with the help of piezoelectric sensors. We can develop, and then further it is amplified, and at the end we can get the information on a user friendly environment with the help of a computer. That is actually the data processing and display portion of this STM. So the first thing what we need to know is the metal tip is also called as the scanning tip is the most important thing, because it's usually made from the tungsten metal or platinum iridium alloy. We're at the very end of the tip, and there is one atom of the material at the very end of the tip. You see, it's really very thin, because it has been considered that there is a single atom at the final end of the tip. So the scanning tip is the most important aspect of STM, as the tunneling current is carried by that. So it's moved about the surface of the sample, so the electron can tunnel. This is actually the barrier, the region in between the sample and the tip. So when the potential difference is applied between the sample and the tip, so the electron may tunnel from the sample to the tip, or from the tip to the sample, depending on the applied bias voltage, and we can get information accordingly. So the other part of this STM is the piezoelectric scanner, because we have piezoelectric material in which create potential difference, which creates some voltage upon stress, or maybe upon length changes are produced, dimensional changes are produced. So the scanner tip is attached to a piezoelectric tube scanner, and the piezoelectric effect is a phenomena under which the material changes length accordingly when put onto an electric voltage. So the current is produced due to the tip, and this current can be detected with the help of piezoelectric tube, and that create accordingly the line changes. You see here this is the initial length. When a voltage is applied, the length has been increased or decreased depending on the bias voltage. So by adjusting the voltage on the piezoelectric element, the distance between the tip and the surface can be regulated, and the piezoelectric crystal expand and contract very slightly depending on the voltage applied voltage. And this principle is used to control the horizontal position, that is the XY position, and the height of the scanning tip. So this is something about this is the tip, and this is the piezoelectric tube to detect the voltage changes created due to this tip and sample interaction. So we have the other part, that is actually the distance control and the scanning unit. With the help of this section of the STM, we can control the position using with the help of piezoelectric process, and is very important and play a vital role. So a coarse control is needed to position the tip close enough to the sample before the piezoelectric control can take over. And the final the other part is the data processing unit, that is the computer, and in this section we record the changes that occurred at different portion of the systems, and then accordingly it is displayed in a very systematic order. So the fifth portion of the scanning tunneling microscope is the vibration isolation system, because STM deals with extremely fine position measurement. So the isolation of any vibration is very much important. The tip and the sample, the tip and surface distance must be, and surface of the sample distance must be maintained in around 0.1 angstrom to get desired atomic resolution. And due to the extremely high sensitivity of tunneling current between tip and sample surface height, it is absolutely necessary to reduce inner vibration and to isolate the system from external vibration. So the damping can be achieved by pneumatic system, spring system, or the eddy currents. We need to discuss the working principle or the working procedure of the scanning tunneling microscope in this slide. This is a bit complicated, but anyhow we have different sections, and we need to discuss each of them in detail to understand the working of STM. This is the vibration and isolation system of the STM. So first we need to apply the bias voltage. I mean the external potential difference is applied, and the tip is brought close to the sample by core sample to tip control. What happens at close range between the sample and the tip, fine control of the tip is in all three dimensions near the sample is typically piezoelectric, maintaining tip sample separation of about 4 to 7 angstrom, that is actually 0.4 to 0.7 nanometer range. So what happened in this case, the voltage bias will cause electron to tunnel between the tip and the sample. I mean the tunneling effect occurs, which we need to do. I mean by the application of the applied voltage would happen, the tunneling effect occur. I mean the electron may migrate or may tunnel from the sample to the tip, or it may migrate or tunnel from the tip to the sample depending on the bias voltage. So once tunneling is established, the tip bias and the position with respect to the sample can be varied, and data can be obtained at the computer front. I mean the data processing and display unit, that is actually the computer. So what happened, and if the tip is moved across the sample in XY plane, so the changes in the surface height and density of state cause the changes in the current that could be detected with the help of the piezoelectric section. So these changes are mapped converted into images. So this change in current with respect to the position can be measured itself. That is actually the Z direction, that is actually the distance between the tip and the sample, that can be easily measured. So we have two different modes of working on the STM. One is the constant height mode. I mean we keep the constant height between the sample and the tip, and the other is the constant current mode. We need to elaborate both these different modes of the STM in detail. The first one is the constant height mode. So this is actually the height or the distance that is represented by d in between the tip, this is the tip, and the sample. So what happened, the voltage and height are both held constant while the current changes to keep the voltage from changing. So what happened, this leads to an image made of current changes over the surface, which can be related to the charge density. So it will benefit to using a constant height mode that is faster, as the piezoelectric movement require more time to register the height change in constant current mode. So what happened, this constant current mode is applicable only when the sample is really very flat, because the corrugations more than 6 to 7 angstrom will lead the tip, and generally less preferred due to the risk of damaging the tip. The second is the other mode of the working on the STM, that is the constant current mode. In this case we keep the current constant, and the feedback electronics adjust the height by voltage to the piezoelectric height and control mechanism. What happened, this leads to a height variation, and thus the image comes from the tip topography across the sample and give a constant charge density, and this means contrast has been developed in the image due to variation in charge density. This is actually the tip of the sample, and this is the sample, and this is the separation d in between the sample and the tip. So this process is comparatively time consuming, and because the feedback control has to adjust the current constant according to the height as the tip move along the specific surface. So we need to vary the height between the sample and the tip in this particular case, and only need to keep the constant, to keep the current constant. So we have some advantages of STM from the other traditional microscopes, and some disadvantages as well. So in the advantages sections, we need to know that STM is very helpful because it gives a three-dimensional profile or image of the surface, and which the researcher can easily understand the roughness and surface defects in the samples. This system, the sample obtained from the the image obtained, the STM is capable of capturing much more detail than other microscope, because it's actually 3 dimensions, so it helps researchers better understand the subject of their research on molecular level. And STMs are also versatile, that can be used for ultra high vacuum, air, water, and other liquid and gases. So it can activate. They will activate temperature as low as 0 Kelvin up to few hundred degrees Celsius. So scanning tunneling microscope work faster than atomic if you compare the STM with AFM, so scanning tunneling microscope is comparatively faster than atomic force microscopy. So atomic force microscopy, the maximum sample size is around 150 multiplied by 150 micrometer, but in case of STM generate millimeter size sample and width. So finally, the resolution of STM is much higher than atomic force microscopy. We had some disadvantages as well. Some of the disadvantages is that STMs can be difficult to use effectively, because we need a specific techniques that require a lot of skills and precision. Special qualified person are need to operate the STM. So STM requires very stable and smooth surfaces, excellent vibration control, and because these piezoelectric sensors are applied over here, so these systems must be placed in a very excellent and a smooth surface, so that there is almost minimum or zero vibrations that is affecting the other part of the systems. So STMs are highly specialized equipment that is fragile and expensive compared to the other systems. So STM analysis is only used for conductive material, as we discussed before, is only used for conducting material. But if we observe the FM, that can also be used for non-conductive material as well. For insulating material. So STM require vacuum atmosphere. The atmosphere needed for the STM is vacuum, and it can work even in liquid as well. So for the reason AFM can be used for the biological materials. So uses of STM. STM we can use for the STM images are not direct surfaces. Actually is the case of optical, just like we observe in the optical microscopy. Otherwise is a measure of the local density of states of a material as a surface and a function of lateral, that is the xy position of the sample and the energy. So within the sample, each electron has specific energy, and only certain number of electrons can occupy that level, depending on this. So similarly, the distribution that gives number of electron allowed per energy levels is a function of certain energy is called the density of states. So the grayscale image generated is direct measure of atomic variation of the surface. So this is something what we can do with the STM. This was some discussion about the STM, and that brought another improvement in the magnification for the characterization of different sort of materials. So I hope we can discuss something new in the next lecture. Thank you very much.